Hello, these are the Exam 3 review slides for Fall 2017, stuff like that. So, first up, we've got compounds. We need to see if they are aromatic, anti-aromatic, or non-aromatic. Okay, so you know they're non-aromatic because as you go around the ring, okay, each atom that's part of the ring has to either have a charge, with some exceptions, have a lone pair, or be part of a pi bond, either a double bond or triple bond, stuff like that. And so if you go around here and something doesn't have that, then you know it's automatically going to be non-aromatic. If they do, then you need to count how many pi electrons here. So for aromatic, so the easiest way that I know how to do it is to just sort of make a table. Okay? We know that benzene is the classic aromatic, and it has six pi electrons, right? So what we're going to do is we're going to bounce back and forth here. So 6, 8, 10, 12, 14, 16, 18, 20, and so on and so forth. You can also go backwards, right? So 4 and 2, right? So you're going to sort of bounce it, right, down here, and so on. Okay, so you're going to go back and forth. Then you don't have to remember the numbers. You can just write this out quickly. Okay. So for here, right, all 4 of these carbons are part of a double bond, right? So we have 2 here, right? So we have 4 pi electrons, okay, total. So that would make it anti-aromatic. So for here, right, every carbon is part of a double bond. It's benzene, so it better be. So 2 here, 2 here, 2 here. So 6 overall, so it better be aromatic. Okay, so we have 2 here and 2 here, right? These 4 carbons are all part of a double bond. The oxygen has lone pairs, so it's definitely not non-aromatic. Now, when it comes to figuring out if you have to count the lone pairs, if it's on a carbon, lone pair on a carbon, you have to count it. No way around it. But for anything else, what the molecule is going to be able to do is it's going to be able to flex and be able to say, okay, how do I become aromatic? Okay, so right now we're at anti-aromatic because there's only 4. Okay, but if I put one of these sets of lone pairs in here, then it can become 6 and it can be aromatic. So what it does is it sort of the extra set. What it does is it puts them 90 degrees away from where the other p orbitals are, so you can basically hide them. Okay, and so the molecule is going to, now again, for carbon you got to count the lone pairs, but everything else it's going to either put them in or hide them so that it can become aromatic. Okay? Look at that. So for this one here, right, double bond, double bond, double bond, and this right here, right, this is just CH2. Right? This carbon here, it doesn't have a charge, doesn't have a lone pair, doesn't have it's not part of a pi bond. So this right here is just regular sp3 hybridized, so you can't go all the way around the ring with that. So this is non-aromatic. Okay, so for here, right? So there's that list of base structures that you need to know for naming benzenes. And so for here, the base structure is actually right here. Okay, so this is phenol. Okay, so this ends up being the side chain, so chloro. Now, when you have a base structure, this is always going to be number 1. Okay, wherever that group is attached, it's going to be number 1. So you're going to want to either go you want to see what the numbering looks like clockwise and counterclockwise. So we go clockwise, it comes 2, 3, 4, 5, 6. So the chloro is at 3. The other option is to take this at 1 and then go counterclockwise. So 2, 3, 4, 5, 6. So 5. So we're going to want to take this numbering here. Okay, so it becomes 3 chlorophenol. Now for this one, okay, there's no base structure. Okay, it's just going to be benzene. When that happens, what's going to each one of these side chains has a chance to be number 1. Okay, so we have a chloro and a nitro. So if we had the chloro be number 1, you're going to want to go either clockwise or counterclockwise towards the nearest neighbor. So the quickest way you can get to somebody else. So that would be this way. So it would be 1, 2, 3, 4, 5, 6. Right? So it would be 1, 3. Okay. Alternatively, if you said this was 1, we'd want to go counterclockwise to get to the chlorine faster. So 1, 2, 3, 4, 5, 6. So 3, 1. You add them up, 4 and 4. Okay, so there's no other way that we can do this, break this tie. So if someone, we can do another type of numbering where it would be a 3, it'd add up to a 3, then we pick that one. But there's no other way that we can do these, do the number sets or whatever to get anything lower. So here, the chemistry gods have decreed that when there's no other way to break the tie, then the first alphabetically gets the 1. Okay, so becomes so we're going to use these numbers. Okay, this is an exception. Okay? So it becomes 1 chloro, 3 nitro, benzene. Now, with the electrophilic aromatic substitution, the bromination. Okay, so again, this happens in 3 steps, and I'm going to want you to write the resonance structures. Okay, so the first thing that's going to happen is going to be this set of lone pairs is going to attack the catalyst. Right, this is a Lewis acid catalyst, and then when it does that, it's going to rip these electrons away from it. So remember that probably 95 times out of 100, when you have a catalyst in here and you're supposed to draw a curve arrow mechanism, the first step is going to be is some sort of interacting with that catalyst. It's almost always the case. So you end up with a Cl minus, right? Because these 2 electrons have gone with the other chlorine, and so it has a plus charge, and so FeCl4 minus. Okay? Now that's the first step. Second step is going to be, right, so it's going to be the benzene attacking the Cl plus. Okay. Now, I told you, right, so it's got lone pairs here, so it's an orthopair director. I've also told you that that's where the chlorine is supposed to go. So we got chlorine, hydrogen, OH, like this. Now this carbon here only has 3 bonds, so it has a plus charge there. Okay. So now we can do resonance structures. Okay. So we can move this to there. Okay. Put the plus charge there. Now we have 2 options. Okay, we could move that up there to get this, and so there's an H here, right? So puts the plus charge there. The other option, okay, would be to set this pair of lone pairs down to help out. Because it's orthopara, right, you have this extra option. It's going to be able to utilize those lone pairs in an extra resonance structure. So it's going to look like this. Okay, so you have these different resonance structures. But to get to the final product, whatever was negative here is going to come in and grab the hydrogen wherever it is that you added, right? Because we can only have one thing attached to each carbon of a hydrogen. Right now we have 2. Right? So it's going to grab that hydrogen. These electrons are going to collapse down, and you're going to reform the benzene here. They work. They all work exactly the same. Now, just as a reminder, for directing group strategies, okay, this didn't print out very well. If you have N double bond O, C double bond O, S double bond O, C triple bond N, let's say N plus, right? These groups here, these are meta directors. Okay. So about that. So the orthopara, right? Those are going to be things with lone pairs. Okay. So this is always going to be right next to the ring, adjacent to the ring. Okay. These are going to be lone pairs adjacent to the ring, to benzene. Or it's going to be an alkyl group. Okay. So that's how you'd be able to figure out. Now, these are activating, these are deactivating. Now, the halides are kind of weird because they do have lone pairs, so they're ortho-pair directing, but they are deactivating because they're so electronegative. So you have to be kind of careful with that. Okay, so right here, right? So we're adding the chlorine, we're adding the chlorine to it. Where does it get directed to? What's on the ring is what directs it, the new thing to come in, right? So this is an alkyl group, so it's going to want to go ortho or para. Okay, so CH3. So we're going to get one set where it's ortho. We're going to get another where it's para. Now for here, we have the C double bond O directly next to the ring, so it's a meta director. Okay, so it's going to either go here or here. So two away from the group. Here it's either one away from the group, the ortho, or across from it. And so the chlorine will go here. Again, it's you could have put it on this side. It's not a big deal because it's the same molecule, just flipped. You're going to be some of these picked reagents, right? So you have this list. I actually think I just copied this list onto the test. So with that, so if I'm going to put a chlorine directly onto the ring, right? So with that, so you're going to use B. Right? You need to have that Lewis acid there. Just regular chlorine isn't going to do it. Now, if you want to put a bromine on the ring, you'd use this. Okay, but if you want to put onto a next to the ring, right, an alkyl group next to the ring, then you'd need NBS, N-bromosuccinimide. Now for this one here, you're going to put the sulfonic acid. So you need this. This group was with an sulfuric acid catalyst. So, all right. And last but not least, you're putting on the fluoro group here, so you're going to need to put the FT in. So there you go. Not too bad. Now for design of synthesis, okay. Now typically what you're going to want to do is you're going to want to say, okay, we're going to have to go through two paths. There's two potential ways that we could do this. Okay, so you can either have the NO2, we can either go through this intermediate, or we could go through this synthetic intermediate, right? So don't forget there's lone pairs here. Okay, so NO2, right? So this looks like that. So you have an N double bond O right next to the ring, right? So that's going to want to, that's a meta director, so it's going to put there. So we can't put the chlorine. If we put the chlorine on, here we get the meta. But here, because we have the lone pairs, we have a set of lone pairs next to it, these are ortho para. One away and across. So we can put the nitric group here. So we know that we have to go through this intermediate, and the last step is going to be HNO3, H2SO4. So we know the last step is that. So to get that chlorine on there, we have to use Cl2 FeCl3. We have to put the chlorine on first, and then put the nitro. If we did the opposite way, we'd end up with the meta. So, now, you assume that, if you did this in the lab, you get a mixture of the ortho and meta isomers. We're just going to assume that you can isolate them, and you can separate those. That or it just magically goes to it. Okay. Now, for this one, so we have, we're going to use Beer's law, which is A equals the extinction coefficient times the path length times the concentration. Okay, so in here, so we know that the coefficient is 6,300. That's just something you look at the big table of coefficients, or what everybody else does. You could look at Google or Wikipedia. The path length almost always is going to be 1 centimeter. Okay, and the concentration is what we're looking at. What's the concentration? The absorbance, right? So is 0.025. Okay, so we're just going to do some basic math, some basic algebra. 6,300 molar, and so that ends up being, I think, 4 times this to the minus 6th molar, which is, if you want to get really fancy, is 4 micromolar. So I'm pretty sure that that's right. So this part is. Okay, now these right here. So these you always do the same way. So you're going to get 4 different products. So what you do is you say, okay, I've got the diene here. So we're going to take one of these, the double bonds, and attack the hydrogen. That's going to kick these electrons off onto the chlorine. Okay. So you're going to end up with a hydrogen adding here. Right? So there's a hydrogen. We're going to put this hydrogen here so that the H plus can go there, because you want the carbocation to be next to the other double bonds, because you can get a resonance structure with it. Okay, this can go there to help you out. So that moves that there, and now the carbocation is there. If the chlorine sees this resonance structure, it's going to attack there to make this. If it sees this resonance structure, it's going to attack there to make that. Now, we're going to do the same thing, except we're going to use this double bond. Same thing attacks. So it goes over here. Right, so hydrogen, right? So hydrogen here, right? We're going to put that third hydrogen here to make the CH3 group. We didn't do anything with that double bond, right? And when we react here, so since this carbon has 3 bonds, so it's going to be like, you got to have a plus charge, plus Cl minus. Okay. Again, you can do a resonance structure where that moves over. So that moves over here. So now this carbon gets the positive charge. Okay. So if the chlorine sees this resonance structure, it's going to attack there. If it sees this one, it's going to attack there. And those are your 4 products. I didn't say there's 4 possible products. I'm not going to ask which one's the major product because it can get complicated in a hurry. So about that. But that's how you do all of them. You start off with one of them. One of the double bonds attack with the hydrogen on. You're going to put that positive charge right next to the other double bond, do the resonance structure, and then have the chlorine attack where that positive charge is. Now, then you reset, go back to this molecule. Now instead you attack with this double bond. And then again, you can do the resonance structure. You're going to want to put that charge right next to the double bond, do the resonance, so you can get the resonance structures, and then have the chlorine or bromine or whatever it is come in and attack. Okay, that's how you do them all. Now, for the Diels-Alder, right? So for here, Remember, you've got, always makes this 6-membered ring. Okay. So these 4 carbons of the ring are going to be your dienes. So that's going to be like this. Okay. These 2 carbons are going to be your dienophile. Okay, those 2 carbons. But notice how these groups here, they're both on wedges. So that means they must be on the same side. Okay, so then hydrogens must be over here. So this is what you're going to need. This plus that. Now, reactions to know. Okay, so again, we're going to end up having, right, we have the diene, we have the dienophile. Right? Remember, this is going to go here, it's going to go there, that's going to go there. These groups here and these groups here are going to follow. So if this is a wedge, if these are going to be on the wedge, then these are going to be on the dash. Okay, they have to, or vice versa. Okay. So by that, now on here, so it doesn't really matter. Down here, when you have a cyclic diene, then it does. Okay, so you have a CH2 here. This thing has to get out of the way. Okay, so another way that you can draw this. Right, so the mechanism is still the same. So it's there, there, there. So this CH2 is going to still connect between these 2 carbons. Okay, but it's got to get out of the way. Right, it's got to push out of the way. So these 4 carbons can react here. Okay, so here's those 5 carbons there. Okay, I usually say that it's on a wedge, moving up. So that means what you have to do is you have to look at this this side here, and you have to figure out. Well, you say look at the dienophile and say, okay, is there anything that has an extra pi bond in it? Yep, it's right here, the C double bond O. So what that means is that this is going up. So if that's going to be a wedge, that means this side here has to be a dash. Okay, which means these hydrogens have to be on the wedge. So this side has to be a dash. So you end up being this. Sometimes it's easier to look from the top, as opposed to looking like this. But either one's perfectly valid. Okay, so for this one, first to note, right? So usually what's going to happen is the benzene is going to attach to where the chlorine is. Okay, whether it's here or here versus here. Okay. Now, you do have to be careful with the alkylation that you don't, because remember we go through a carbocation intermediate, you can get a rearrangement here, a hydride shift to make a more stable carbocation. So be careful about the alkylation. Acylation never happens. So these are the what you can do, the fluorination, chlorination, iodination, like that. So put those halides on. Okay, to put the nitro group on here, you need a lot of nitric acid and a little bit of and some sulfuric acid. That'll put that NO2 group on here. If you instead you have SO3 in the presence of sulfuric acid, you put the sulfenic acid. Now for these, you have to remember, so for KMNO4, in the presence of benzene, if you have a CH bond here, right adjacent to the ring, what's going to happen is the rest of the chain is going to be locked off, and you're going to end up with just a carboxylic acid here. Right? So it's going to look like that. Okay. Now, if you had a T-butyl group here or something like that, that would be unaffected because you don't have a CH bond here. It's just a regular carbon. Same thing goes with NBS. Okay. So if what you're looking for is there a CH bond here? Yep, there's CH bonds here. So we're going to swap out one of the hydrogens for bromide right next to the ring. So for her hydrogenation under normal conditions, you're just going to, it's just regular hydrogenation. You're going to take down the alkene, but the benzene is going to be unaffected. In order to be able to reduce down the double bonds of the benzene, you're going to have to really hit it hard. And so something like 100 atmospheres of pressure with that. So now, alternatively, if you have, and this is a special case, if you have a C double bond O right next to the benzene, you're going to swap that out for a CH2. And it's a very special case. If it's somewhere else, the acetyl window is remote from the benzene, then it doesn't work. It only works when it's right next to the thing. Now, the other way that you can do that same reaction, swap out a CH2 or acetyl window for a CH2, is either with Wolff-Kishner, which is hydrazine under basic conditions, or with a Clemmensen reduction. This is a zinc mercury amalgam in the presence of acid. Again, they're going to swap out acetyl window for a CH2. Now, these are more general because you don't have to have the benzene around. And the reason why we have 3 different ways is to do the exact same thing is as the molecule gets more complicated, some groups are going to be more sensitive to acid or base or hydrogenation, things like that. So you have to take that into account. So it's good to have different ways of doing the same thing to give you flexibility. So good luck.